Here we have a position function. We can tell it's a position function because we're given the position as a function of time, and we want to take this position function and show where the particle is at these different indicated instances. So we have 6 different number lines here, and we can use that to represent where the particle is at each one of these points in time. One thing that we'll look at, we don't have numbers on these number lines, so we don't have to be exactly perfect, but we can look here. The maximum value that we have is about 400, so we can imagine 400 here and negative 400 to give us kind of a guess of the size or scale that we're using. So if we look at particle A, the first thing that we want to do on our number line is to locate where the particle actually is. Notice it's just below 0, and 0 on the graph here represents 0, the origin on the number line. So if we're just below, just negative of 0, that means that we are just barely to the left of the origin. The other things that we're looking at besides the position, which we can read directly off the graph by looking at what the position is of each particle, we're also looking for the velocity and the acceleration to have a full motion diagram here. Our velocity shows up as the slope of the tangent line. We can sketch that here because the velocity is the derivative of the position, so it will show up as the slope of the tangent line. The acceleration is the derivative of velocity, so that means that is the second derivative of the position, and that second derivative shows up as concavity. So you can kind of imagine a parabola there, and we can see the concavity. So on a graph like this, technically we could estimate the values pretty well, but this number line is measuring distances in meters. We can really make the velocity and the acceleration any size that we want to because we're mapping a different set of units, meters per second or meters per second squared. We're mapping that different set of units onto a number line that's just measuring meters. So really we're more interested in the relative sizes of the velocity and the acceleration. Here we see that the velocity is tilted downwards, and so that means that we have a negative slope here because the slope of the tangent line is directed downwards, and so we can give ourselves a velocity vector there. And in this case, we notice that the concavity is upwards. If we're concave up, that means that we have a positive acceleration. This is a pretty wide parabola, and so a wider parabola means that we have a smaller acceleration because it's taking longer for us to change direction. So we have I did this backwards. We have a negative velocity, so that should be this way. It's pointed to the left, and we have a small positive acceleration. So at this one point in time, we can tell where the particle is on the number line. We can estimate what its velocity is based on the slope. We can estimate what its acceleration is based on the concavity. Take a moment to pause this video and try to answer the rest of these using the same process. Looking at particle 2, we can see we're at about a negative 100 there. If we used our scale of saying that this was about negative 400, this would be negative 200, this would be negative 100. Would be about there. The next thing I look at is my velocity. My velocity is the slope of the tangent line, and notice here at a min or a max, the velocity equals 0 when you have a horizontal tangent line. So my velocity here is 0. I'll indicate that with saying that the velocity is 0. And then I can look here, I have the same curvature the whole way. So whatever concavity I had at A, I still have that concavity at B. It's still small and still positive. So I'm going to say I have the acceleration, the same acceleration that I had before. I'm going to try to draw it about the same size. Basically what we're seeing here is we're moving to the left, but we have a positive acceleration. So we're slowing down. We stop here for a moment. Our velocity is 0 at this instant, but we still have a positive acceleration. And so in our next instant, now we start speeding up, going back to the right. That's our interpretation there. Looking at point C, we can see at point C, we're exactly right on this time axis. So that means that we are right at the origin. I can look at the slope of the tangent line here, and I see that I have a positive slope. This positive slope is essentially the same upwards incline as much as this one was downwards. So I'm going to try to make my velocity vector approximately the same size here, but since it's inclined upwards now, that means it's a positive velocity and that we're moving to the right now. Also notice here, this point is more or less right on that part of that parabola. And so we're going to say for this instant right here, we still have a small acceleration, a small positive acceleration, just like we had before in the previous 2 points. But you can notice right here that that curvature is diverging, and so probably in the next second or two after we're at location C, that's when the acceleration disappears. Then we move on to position D. Looking at position D, we can see where our position is. It's a little bit past 200, so we'd be a little bit past halfway. We can look at our velocity here as the slope of that line, and we see that our slope is a little bit steeper here than it was at C, so our velocity vector is going to be a little bit bigger than it was at C because we're moving a little bit faster. Also notice when I draw this tangent line, the tangent line falls right along the line because this is a straight line. There's no curvature here, and so if I have a straight line with no curvature, that means that my acceleration will be 0 there. There's no acceleration for a straight line. There's only acceleration when we have a parabola, because the acceleration is that second derivative. I can then look at point E. At point E, I can figure out my position is about 400, so I'm going to be all the way over here at the end, because I'm at positive 400 there. I look for my velocity, that's the slope of the tangent line. I have another max or min here, so my velocity here is going to be 0, the null vector. And then when I look for my acceleration, I again try to sketch a parabola, and I see that I have a concave down parabola, and it is narrower than the other one, so this is a larger acceleration than I had before, and this is going to be a negative acceleration because it's concave down. You can also see the interval where I had 0 curvature, where I had constant acceleration there. So here I have a larger negative acceleration, so I'm going to draw my acceleration vector bigger than this one, maybe twice as big, because this is about half the width, and it's concave down, it's negative, so it'll be pointing to the left. And then finally, when we look at point F is back on that axis again, so I'm back at the origin. I can look at my velocity, and my velocity there is very steep. It's the steepest velocity that I've had anywhere, so I'm going to have the largest velocity vector. It's inclined downwards, and so it's going to be a negative velocity vector. It's going to be pointing to the left. And then notice that the curvature at E and F are the same, so I have the same curvature. I'm going to try to draw the same acceleration vector. So here I can take a position graph, and I can look at the point of the particle, as measured on the position axis there, and I can map that onto a coordinate system, and I can figure out where the particle is at each instant. I can use the slope of the tangent line to estimate the velocity of the particle at each instant, and I can estimate the curvature of the graph to give myself an idea of what the acceleration is at each instant.